Okay, yeah, we're very happy to have Wang from UCLA to give us a colloquium, and she'll be talking about restricted projections to planes in R3. And then after the talk, we'll have a few announcements. So please, when you're ready, Hong.
Okay, thank you very much for the invitation. It's a great pleasure and honor to speak at the Happy AIM talk. I will be talking about restricted projections to planes in R3. And this is joint work with Sherman Gan, Xiaoming Guo, Larry Guth, and Terry Harris, and Dominic Maradak, who is an organizer here. Please feel free to stop me at any time in case you have questions. So we'll start with talking about orthogonal projections. Let theta be a unit vector in Rd, and p theta is defined as the orthogonal projection from Rd to the hyperplane that's perpendicular to theta. So the picture is we have some set here E, and then we are given a direction theta. Then we try to project E to the plane that's perpendicular to theta, to the hyperplane. So this is the projection image of E. So that's the definition is x and x minus, so x dot the unit vector times the theta. So minus the path that's in direction theta. Mastrom's projection theorem says that so on this page everything is in R2. So on this page everything is in R2, and so we have the Mastrom's projection theorem back to 1954. Says that if E is a Borel subset of the plane, then for almost all unit vector theta, the Hausdorff dimension of the projection image, the projection of E along theta, equals to the minimum of the Hausdorff dimension of E and 1. So this is the best possible because now the theta, this perpendicular plane is just a line, and the theta. So the maximum dimension is 1, and also the best we can hope for is the dimension of the E. And then after that, Paris and Schlag, they proved a result about exceptional set, meaning that the set of theta such that the projection image is small should have bounded dimension. So let sigma be any number between 0 and the minimum of the dimension for E and 1. Then the Hausdorff dimension of the set of the directions such that the projection image has dimension less than sigma is bounded by the maximum of 1 plus sigma minus the Hausdorff dimension of E and 0. So what does it mean? Here we can think of, so the result when the Hausdorff dimension of E is strictly greater than 1 and sigma equals to 1 is due to Faulkner in 1982, says that, okay, suppose that our set E, it has a large dimension, then intuitively the set of directions such that the projection image is small should have small dimension. So there won't be many theta such that the projection image has a small dimension. And this quantity quantifies how small the set of exceptional set will be. And there is also another generalization of Marshall's projection theorem that's due to Kaufman in 1968. Says the setup is essentially the same as this theorem, but the difference is that here one can think that the Kaufman's projection theorem works more like for the set of for our set E that has dimension less than 1, and then the set of directions such that the projection image is small is bounded by the sigma itself. So in other words, so the set of directions with a small projection image should have small dimension depending on how small the projection image we want to impose the condition. Okay, and in this talk, we'll provide a corresponding theorem of Marstrom and Paris and Schrag in R3 when we restrict ourselves to a set of direction that lies on some non-degenerate curve in R3. Okay. So Matila generalized Marstrom's theorem to higher dimensions. So he showed that in RD, then for almost all theta in for almost all unit vectors, the projection image has dimension equals to the minimum of the dimension of E and D minus 1. So the question that we ask, so actually asked by Faster and opponent, says that when, sorry, this is 3. When dimension D equals to 3, do we need all theta in S2? So what about theta on some curve in S2? So suppose that we have some curve gamma here, and then if we only consider the set of directions theta on this gamma, and what can we say about projection image? So if we don't impose any condition on this curve, here is a degenerate example. Let's suppose that this gamma is the equator. So it's this great circle, and E is a subset of the XY plane. So E is here. So imagine everything that is in R3. Then since our direction is theta lies also on this plane, is perpendicular to this plane. And then when we consider the orthogonal projection to the theta perp, then the image of E will be on the line that's the intersection of theta perp and the XY plane. And when we consider our theta on this equator, then it means that this theta will still be parallel to this XY plane. So any projection image will be contained in a line. And in particular, when the Hausdorff dimension of E is strictly greater than 1, well, since the projection image is contained in the line, then the Hausdorff dimension is less or equal than 1. So this is a degenerate example showing that an analog of this is not true. However, if we rule out this degenerate example, so this is a conjecture by Vassler and opponent in 2014, says that if gamma is a non-degenerate curve in R3, non-degenerate meaning that the determinant of gamma theta and gamma prime theta and gamma double prime theta is non-zero. So in other words, it's kind of like a spatial curve. And maybe spatial is not the right word, but it says that one can try sort of imagine gamma is away from any of those great circle. Now, for each theta in the unit interval, we can consider two types of orthogonal projections. So the first type, we consider rho theta, that's from R3 to R, that's X, maps to X dot gamma theta. So when this curve is clear from the context, sometimes we will use theta in the parameter space, identify the theta in the parameter space and the image gamma theta. So here this rho theta is X maps to X dot gamma theta, and that's so project to this line. And so this pi theta is more like what we studied before. So X R3 maps to the plane that's perpendicular to gamma theta. So that's X minus component on this direction theta. Then they conjectured that the Hausdorff dimension of rho theta E equals to the minimum of the dimension of E and 1 for almost all theta on the plane. For almost all theta on the unit interval. And then the Hausdorff dimension of this pi theta E equals to the minimum of the Hausdorff dimension of E and 2 for almost all theta. So this result is like Master's projection theorem in R3, but the difference is that we restrict now a set of directions on a non-degenerate curve on the unit sphere. But previously in Master's theorem and also Matilda's generalization, we only consider we are allowed to choose all possible unit vectors. So a typical example is this gamma naught. So is a small circle that's defined by theta maps to cosine theta over square root of 2 and sine theta over square root of 2, then 1 over square root of 2. So it's here. So this is the gamma naught. So this example, this gamma naught is a typical example of a non-degenerate curve. And it was proved by Kamarki, opponent, and Venieri in 2017, where they proved the first part projection to a line for this particular curve gamma naught. This curve is nice because it's like the light cone intersect the unit sphere. And then very recently, by Pramanik, Yang, and Zhao, they proved the first part of the conjecture for general C2 non-degenerate curve. And for the second part and other works related to this conjecture includes some results by opponent Venieri, and Harris and Chen. So the results that I'm going to present today is about the second part of their conjecture. So let E be a Borel subset in R3. Then the set of theta inside the unit interval, which we identify with this curve. such that the Hausdorff dimension of pi theta e, that is, so this is gamma theta. So pi theta is the orthogonal projection to gamma theta, the plane that's perpendicular to gamma theta. The set of theta such that the projection image is smaller than sigma is less than the maximum of 1 plus sigma minus the Hausdorff dimension of E and 0. So the form of this result is really an analog of the result by Paris and Schlag for the Mastrom's projection theorem. And as a corollary, so we have that for almost all theta, the Hausdorff dimension of pi theta e equals to the minimum of the Hausdorff dimension of E and 2. So this is an analog of Mastrom's projection theorem for curve, for the set of directions in the curve, in the non-degenerate curve. And we also have a result about the Lebesgue measure, meaning that if the Hausdorff dimension of E is strictly greater than 2, then the Lebesgue measure of the orthogonal projection image is positive.
This is for almost all theta, right?
Yes.
Okay, yeah, thanks.
Okay. Are there any questions so far? Okay, so so the proof idea is we use instance for tubes, and we use the Fourier analysis method to study instance for tubes. So let's rewrite the proof of Mastrom's projection theorem using this instance. So the statement of Mastrom's projection theorem is after some reduction, it's equivalent to the following instance problem. So let m be a large integer and s be any any number between 0 and 1. So here we let's just prove the part for the dimension of E between the dimension of E is between 0 and 1. For the other part, the proof is similar, and then we will not present it in the talk. So now let E be a set of n to the s many unit balls in a ball of radius n in R2, satisfying BR intersect E has the number of unit balls in BR is less than R to the S for any BR. So perhaps you are more used to the setting where E is a set of delta balls where delta is small in the unit ball, and then the intersection and the intersection between any small ball and the unit and E has a small volume. So this is just a rescaling of the problem, a rescaling of the ball condition that maybe some people are used to. And this, considering E as a set of a union of unit balls, maybe a union, is more convenient for later when we calculate the two integrals. And let omega be a subset of the unit circle, which is a set of 1 over n separated directions. And the cardinality of omega is greater than n. So this is like omega. And then T is a set of distinct 1 times n rectangles of length n and width 1, satisfying for any x in E, there exists a subset omega x such that its cardinality is also about n to the minus 1. And for any theta in our subset omega x. So for simplicity, this statement, this condition, this assumption, you can just think that, okay, for any x in E and for any theta in omega, there exists a tube in our collection such that this tube is in the direction theta and contains x.
So should be n instead of n inverse, right?
Right, thank you.
Yeah. Okay, thanks.
So if T satisfied this assumption, then the Mass-John's projection theorem is equivalent to the statement that the cardinality of the tube must be greater than the cardinality of the set of directions omega, that's n, times n to the minimum of s and 1. So in this case, since we already choose our s to be between 0 and 1, let me just write s here, sorry. So why this is the case? So suppose that Mass-John's projection theorem is not true, then we will have a set of omega of cardinality about n, and then for each direction in omega, so the projection image of E is small. That means that we can cover the projection image by say n to the s minus epsilon many unit tubes. And then let T be the union of those tubes. So for each theta, there will be less than n to the s minus epsilon many tubes that can cover E. This is equivalent to the statement that the projection image of E along theta is small. And then we take T to be the union of those theta. Then we can say that the set, the number of tubes in this T will be less than n to the 1 plus s minus epsilon. And this will contradict our instance bound. So this is we prove by contradiction. So suppose that this is not true, and then this bound should not hold. So what we were just saying is that the right-hand side implies the left-hand side, and the converse is also true by if we can just reverse our reasoning. So are there any question about the setting? Okay, now let's study the instance bound. So the setting before says that we have a set E of cardinality n to the s, satisfying that a ball intersect E has those unit balls are not concentrated on any small ball. So this E has some kind of spacing condition. And then on each unit ball in E, there is a set of tubes passing through it, a set of n tubes. And we want to say that the union of those tubes is large. So the number of those tubes is large. So let's take phi t as smooth bump function on t. So phi t is about 1 on t, and it's supported on 2t. And then let's take f to be sum over phi t with t in our collection of tubes. Then the integral of f on our set E, so equals to the number of incidents between E and T, defined as the Ex will be a unit ball in E, and T is a 1 times n rectangle in T, such that X is in T. So the integral of f on E is about the number of incidences between E and T, which equals to, by our definition of T, the number of unit balls times the number of directions. And so we want to give an upper bound on the integral of f on E, and we are going to use Fourier analysis. So the Fourier transform of phi t is supported on the dual of t. So the t is a convex set, so it's a 1 times n rectangle. Then t star, the dual, is defined as a thin rectangle of length 1 and width 1 over n, centered at the origin, with direction normal to t. So here, well, the scale of this picture is not quite the same as this picture. So if we are going to use this as 1, then our n will become huge. But anyhow, so this are the large tubes, and the T star is the dual of T. And by basic Fourier analysis, we know that if phi t is a smooth bump function on T, then the Fourier transform is essentially supported. So it's like essentially supported on T star, and then fast decaying elsewhere. So it's decaying very fast. Then let's pick a small constant rho that's about n to the minus epsilon, where epsilon is an arbitrary small number. Then let phi rho b rho be a smooth bump function on a ball of radius rho, centered at the origin. And so the low frequency part is the Fourier transform of phi t and times the smooth bump function on the small ball centered at the origin. And then we take the inverse Fourier transform. And the high frequency part is the phi t minus the low frequency part. So this setting for people in Fourier analysis then you might find it very familiar because in a few recent papers on instance for tubes and also on decoupling and local smoothing, we have used this decomposition and use this method to estimate incidence for tubes. Then we define the high frequency part of f as sum over t, and the high frequency, the phi t high frequency part, same as the low frequency part. So let's rewrite the integral of f on E So it equals to since f equals to f high plus f low, so it's equals to the integral of sum over the two functions. So if the high frequency part dominate, meaning that the integral of f on E is bounded by the integral of f high frequency part on E, an absolute value. So if this is the case, so we split into two cases. The first case is the high frequency dominant. The second case is the low frequency dominant. So if it's the first case, that's the blue part dominant, then by Cauchy-Schwarz is bounded by the volume of E to the 1/2. There is a question. So what do you mean by yeah, that's a very good question. So the high frequency part means that when we take the Fourier transform of phi t, and then we consider the frequency that's outside of a small ball. And the low frequency part is the Fourier transform of phi t with frequency restricted in the small ball centered at the origin. And so, yes, so that's what I was about to say next. In the high frequency part, the tubes do not, so for each omega, the number of those T stars that passes through omega is bounded by n to the epsilon. So on the high frequency part, those T star will not intersect too much. And the low frequency part, they intersect a lot, but we'll prove it in a different way. So recall that F is sum over those tubes, phi t, and if it's the high frequency dominate, then by Cauchy-Schwarz is bounded by the volume of E to the 1/2, and then times the L2 norm of the high frequency part. And as we have discussed, at each point on the support of the high frequency part, the number of T stars that intersect omega is bounded by rho to the -1, where we take our rho to be n to the minus epsilon. So this is really a negligible part, that's n to the epsilon. And now since the number of T star through omega is bounded by n to the epsilon, then we can bound the L2 norm of the high frequency part by sum over phi t square. So this is because they have essentially disjoint support, and then we can use some kind of orthogonality. And since each phi t is like a bump function on t, so phi t square does not really do anything. So we can just replace by phi t. And so this L2 bound, so this L2 integral is bounded by the number of t times the volume of a single rectangle, that is 1 times n. So we have that. And then so recall that the integral of f on E is like n times E. So omega is the number of directions, that's n, that's about n. So if we do some algebra and say this term is bounded by this term, then we can calculate that the number of tubes is greater than n to the minus 2 epsilon times the number of unit balls in E times n. So this should recall that the number of directions is about n. And so this is what we hope to show at the beginning. So this is okay. So in the high frequency part dominant case, this is okay. So we have proved to what we want. But what happens if it's the low frequency part dominant? So in general, for instance problem, if the low frequency part dominates, in our imagination, we kind of imagine the tubes are clustered together. So many thin tubes were inside a thick tube. But in this case, since the set that we are doing integration, our underlying E has dimensions smaller than 1. So this case does not really happen, because what does it mean by low frequency part dominates? So it means that for a typical ball, because so let's say this is the low frequency part, and this has the scale. This is about 1, and the low frequency part is rho to the n to the minus epsilon. That's a relatively small number, and so when we multiply the Fourier transform of a function by a ball of some small radius, it means that on the physical space we convolve our function with something that's up to some scaling, means that we convolve our function by something that's like a constant on a ball of radius n to the epsilon. So in the picture, so suppose that we have our so suppose that this is our T. And then when we are considering the low frequency part, what we are doing, so the F low frequency part compared to F is a sum of bump functions on those T. And then this low frequency part will be like, we consider we have a slightly fatter ball of radius n to the epsilon, and we like convolve everything, make everything to the thickness n to the epsilon. And then and on the value of F, we'll need to multiply by n to the minus epsilon. So this means that for a typical B rho to the minus 1, recall that rho is a small number, so rho to the minus 1 is a large number. And so this is for a typical thick ball intersecting E. The number of T through this thick ball is greater than n times this rho to the minus 1. So this is larger than 1. So this follows from the fact that low frequency part of F dominates on E. So, but this can't be true because our E has dimension less than 1. So it means that the number of unit balls inside of E, inside this thick ball, is less than rho to the minus S. So even if on each point we have n tubes through this point, and we suppose that the tubes do not intersect at all, but we will have at most n times rho to the minus 1 many tubes that's through a thick ball. So dimension of E equals to S implies that this number, the same thing, So implies that this number should be smaller than n2 times rho to d minus s, and s is smaller than 1. So this gives a contradiction. So when we try to understand instance for us on a fractal set, so this says that the low frequency part cannot dominate. And so this finished the proof of Master's projection theorem using this high-low frequency decomposition. And I must say that when we worked on our first paper using this decomposition and decompose into the this method, so we were when we decompose into high frequency part and low frequency part, this was partially inspired by opponent's radio projection paper, where he used some Fourier transform and also have different frequencies. So now it's kind of natural that this can be applied back to geometric measure theory. Okay, now let's talk about, have 15 minutes, and let's talk about restricted projections in R3. So we can consider the same setting. And now, so now for any s between 0 and 2, E is a set of n to the s unit balls, satisfying the ball condition. And T also satisfies that for each x in E and each theta in omega. So here we should think omega as a non-degenerate curve. Omega is a curve in S2. For any x in E and any theta in omega, there exists a unit tube containing x in direction theta. So our set of tubes is defined in this way. So our goal is to show that the number of those tubes should be greater than the number of directions times the cardinality of E. So recall that this omega will be so this omega will be like 1 over n separated directions. So omega is like 1 over n separated set on a curve in S2. And so this is our goal, and we can formulate as before. So F is sum over some smooth bound functions on T, and then the Fourier transform of phi T is essentially supported on T star, but the difference is that this time T star will be a 1 over n neighborhood of plane slab. So T star will be like a 1 over n neighborhood of a 2-dimensional plane. So as before, we can also define the low frequency part and the high frequency part. Low frequency part is defined as we restrict our frequency of phi T on a small ball of radius n to the minus epsilon. And the high frequency part is defined as the outside. But the difference, so the low frequency part, if the low frequency part dominates, then we can use the same method as before to say that this cannot happen. So I'm using this yellow part to denote the low frequency part. And if this dominates, then we can use the same method as before. But here, the high frequency part is way more complicated. The reason why we can prove this theorem is just because omega is like a curve. And so this the high frequency part, even though it's way more complicated, but it still has a one-dimensional nature, so it's kind of doable. But if this omega is no longer a curve and it's some other thing, then the high frequency part might not be as efficient. So let's see why the high frequency part is more complicated. So what we were doing is, in the two-dimensional case, we say that, okay, on the high frequency part, for each point that's outside of this small ball, the number of T star that passing through each point is bounded by, say, n to the epsilon. But this is not true in higher dimensions, just because this T star is like 2 dimensions. So for example, if omega is the equator, which is the degenerate case for projection, and here we are going to see why it's also kind of bad for our method. So if omega is the equator, then there exists omega, the big omega. So maybe I should use gamma here, the curve. And there exists there exists a point, small omega in the high frequency part, such that for any theta on the equator, our point will lie on this, I should say, will lie on theta perpendicular. So here, let me try to explain this picture again. So we have a direction theta, and then we have a tube T parallel to theta. Then our T star is defined as the 1 times 1 times 1 over n neighborhood times 1 over n box. So this is like a slab, a plane slab. This is our T star. But if we can, so this T star by definition is moderately speaking the perpendicular plane of theta. So it's just like 1 over n neighborhood of the perpendicular plane. And then we restrict ourselves to inside a unit ball. So next I would like identify these two. So perpendicular plane of theta and T star, when T is parallel to theta. Then when gamma is the equator, there exists omega such that this omega lies in every single theta perpendicular. So the picture is that we have a theta here, and then this is our theta perpendicular. So when our theta moves on this equator, it's like this, this theta perpendicular plane will rotate. But whenever if they rotate along the equator, then they will contain a common line. That's the line that's perpendicular to the equator. And for any omega on this line, it's contained in the theta perpendicular. So in other words, this is that there are a lot, there is a huge multiplicity for those T stars. So in the equator case, every single T star will contain our omega. And this is different from the planar case, where in the high frequency part, the T stars are morally destroyed. Unfortunately, in our setting, we have excluded the equator. So this is one thing. This example is just to say that why the high frequency part in higher dimensions is more difficult. Now, our key part is to how to understand the high frequency part of F. So because our gamma is now non-degenerate curve, so for simplicity, we will let our gamma to be the light cone intersect our unit sphere. So this will be a small circle, and when we connect with the origin, this will become a cone. And so this gamma is the gamma naught that we discussed as an example at the beginning. So now our theta lies on this gamma. Then what is the theta perpendicular? So the high frequency part of F will be supported on this slab, like out on the slab minus a small ball centered error or at the origin. So the high frequency part is this part. And when our theta moves along this gamma, we will kind of imagine this this slab will rotate in a way that's so it's like stick to the cone. Okay. So in this picture, when our theta is this one, then the theta perpendicular will be then the theta perpendicular will be also be tangent to gamma. But for general gamma, this is not always the case. It will the theta perpendicular will be tangent to a different cone. And so when our theta this T star rotate along, when the theta moves along this gamma, this T star will rotate. In this example, it will be kind of like the slab will be tangent to the cone and then move. And for other directions is here. So this picture, if for maybe somebody knows the square function for the cone, is almost it's very similar to the frequency decomposition in that paper. And we observe that when our omega is far away from the cone, then it's for our T star do not the number of T stars through each omega is like bounded. So if omega is far away from the cone, then there are less then there is only a constantly many theta perpendicular through each omega. But when our omega is very, very close to the light cone, then the multiplicity is higher. However, it's not as high as the degenerate case, the equator that we discussed. So maybe this picture is kind of difficult to imagine. Then let's move this T star to 2 dimension. So this is 1 by 1, and the middle part is the low frequency part that we throw out. So we can estimate as in 2 dimension case. And this part, the blue part is the part that's away from the light cone. So since the number of theta perpendicular through it is bounded, so this part can also be estimated in the same way as before using the two-dimensional case. Now we decompose the middle part diagonally according to the distance to this line, the center line. So here we decompose it to 1/4 and then 1/8 and more. So until we reach the width of n to the minus a half. So this will just be this part. And this red part will be has width n to the minus a half, and the thickness is n to the minus 1. So so the picture is now for each theta, and we identify a red part that has a very high multiplicity, but the advantage is that this high multiplicity lies tangentially to a light cone, and we can. So now we have the difficult part of F, high frequency of F, has frequency lies on the small neighborhood of the light cone, and this allows us to use some free restriction theory, and we can use our idea to estimate this difficult part is to use decoupling for the cone, and then that's the and so we decouple the difficult part of F high into those sectors and then do some estimate. I will stop here. Sorry for the technical talk.
All right, let's thank Hong a lot for her great talk. And yeah, any questions? I'll stop recording here because the video will be uploaded to Happy later.